Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, welcome to this talk. It's my pleasure to introduce Joe Deviati to you. He's visiting us from across the lake from the University of Washington, where he has been a graduate student for the past 5 years. His work lies at the intersection of computer architecture, programming languages, and software engineering. And he's been working on making programs, parallel programs in particular, deterministic. And he'll tell us about that work today.
Great. Thanks, Shaz. So thanks, everyone, for coming to my talk. Really appreciate it. So today I'm going to try to convince you that there's no such thing as luck, at least when it comes to parallel programming, and that we can radically improve the way that we write parallel programs with determinism. So as you all know, we live in an age of parallel hardware, right? Every hardware designer has shipped a multi-core design at this point. Most of the time, it's actually difficult to buy a single-core design, even if you want one. In contrast to this surfeit of parallel hardware, though, there are relatively few parallel programmers who can write the sort of code that efficiently utilizes all of these parallel resources. So why is parallel programming so difficult? Well, first of all, it's difficult because it's programming, right? This is far from a solved problem. All of the single-threaded issues that you have show up again in the context of parallelism. On top of that, if you're writing a parallel program, you generally care a lot about performance. That's one of the main reasons to parallelize. And getting a performant parallel program means you have to deal with things like false sharing, lock intention, scalability, and other complicated issues. On top of that, parallelism introduces its own strange concurrency issues that can affect correctness. So there's a whole new class of correctness bugs out there with scary names like atomicity violations and data races, and these only show up in the context of parallelism. And then finally, I would argue that, as if this weren't bad enough, there's an overarching layer of nondeterminism that really exacerbates the single and multi-threaded correctness issues because it makes execution non-repeatable. So nondeterminism really plagues us throughout the software development cycle. If we want to debug our programs, right, we can't reproduce these so-called Heisenbugs. When we're testing our parallel code, it's very difficult to guarantee testing coverage because of nondeterminism. And then, of course, there are issues that will inevitably seep out into deployment, and then it's difficult to reproduce those back in a development environment. So nondeterminism makes life difficult at every step of this cycle. So I've also done work on correctness issues in parallel programs, but today I'm going to focus on nondeterminism. And I'm going to show you that nondeterminism is not a fundamental aspect of parallel computation, even though all of the multiprocessors and multi-chip processors that we've been building for decades now have been non-deterministic. There's no reason that they have to be that way, and I'll show you some designs today executed in hardware, in software, and also even with small modifications of the programming language that show that we can get deterministic execution for arbitrary parallel programs with relatively low overhead. All right, so here's the outline of the rest of my talk. First, I'll be much clearer about what I mean by determinism, give you some additional motivation for why it's valuable. After that, I'll describe this technique of execution-level determinism, which is a set of techniques we developed at UW that provide deterministic execution for an arbitrary parallel program, even programs that have bugs like data races in them. So I'll show you some algorithms for providing deterministic execution, argue why those algorithms are correct, and then I'll describe how to efficiently implement these algorithms in hardware and in software, and then show you some results from the systems that I've built. After that, I'll talk about some current work that I'm doing, which has some lightweight language extensions to provide higher performance determinism in the context of a software-only system. And then finally, I'll share some of my ideas for future work. All right, so let's get started. What is determinism? So determinism at a kind of intuitive level means that there's one possible output for each input, right? So with a current non-deterministic system, like a conventional multiprocessor we have today, there are many possible outputs for any input. Right? You run your program, you don't really know which one of these you're going to get. With determinism, of course, there would be only one output for each of those inputs. And crucially, the output that you get for any particular input is somewhat arbitrary. It's always going to be the same, but we're going to use this flexibility of not really specifying in advance which of these outputs you get in order to provide higher performance, as you'll see later. So just to make this a little bit more concrete, and since it's an election year, we have this example of a multi-threaded voting machine. Right, so we've got these two threads, blue thread and the red thread. So what they're doing is they're subtracting and incrementing from a shared counter. So at the end of the day, we just look at the value in the counter. If it's positive or negative, we can tell who won the election. Right, so if the code from these two threads of the instructions interleaves at a relatively coarse granularity, then that's OK. We get the expected result that the election is a tie. But if we have them interleaving at a finer granularity, then we have a classic lost update problem, right? And we're going to drop one of the votes. Now, depending on whether it's a red vote or a blue vote that's been dropped, you may or may not consider this to be a bug, maybe a feature. But in the spirit of bipartisanship, let's say that this is some sort of issue that we want to fix, right? So why can these different interleavings arise in the first place? Well, there's lots of things that can affect an execution. From the single-threaded world, we're familiar with notions of input, right? The bytes that you read from a file, or the buttons that a user clicks on. These obviously can affect what your program does. In the multi-threaded world, the number of threads that your program is using can also affect the computation that it performs. But unfortunately, on our current non-deterministic parallel systems, there are many other things that can also affect what execution you get when you run your program. So whether your program has data races in it can definitely affect what happens. Scheduling decisions made by the operating system or even by the hardware can affect things. Even low-level phenomena like temperature can affect the speed with which circuits are switching. And ultimately, that can bubble up into something that's visible in the program's output. And for those of you who have done a lot of parallel programming before, you will no doubt be familiar that the phase of the moon is actually a crucial aspect to getting a parallel program that computes correctly. Right? So ultimately, we could maybe hope to control a lot of these phenomena. Right? Maybe if we didn't believe too much in quantum mechanics, we could control things down to the very lowest physical level. But ultimately, as a programmer, it's very difficult to control a lot of these very low-level things that can affect an execution. Right? Programmers have enough trouble just keeping data races out of their program, let alone worrying about things like temperature. So ultimately, what we want is a higher level, more useful notion of input, like these explicit inputs here. And we want a useful notion of determinism that works for arbitrary multi-threaded programs, abstracting away all these low-level details that can affect an execution, and leaving execution strictly a function of these high-level inputs that a programmer can easily identify and control. So that's exactly the kind of scheme that I'll describe to you today. So just to talk a bit about some of the benefits that determinism could provide if we imagine a world in the future where deterministic execution was deployed throughout our computing infrastructure. So what I have here is I have a little cartoon of the software development cycle. So we do some amount of iterating between testing and debugging. After that, we go ahead and deploy something that we're reasonably confident in. Of course, deployment just reveals new issues, and the cycle starts all over again. Right? So if we had determinism available throughout our deployed computing infrastructure, we'd be able to use reverse debugging techniques while we're debugging our code. Testing results would be reproducible, and this would eliminate the need to stress test parallel programs. Right? We don't have to run them over and over again, hoping to trigger interesting thread interleavings. You just run it once, you get the output that you get, and then you move on to the next input. Because we would have a guarantee that programs would behave the same way from testing on to deployment, testing would ultimately be more valuable. And so we would be deploying code that would be more robust, that we'd have more faith in. And then finally, for the issues that did leak out into production, we'd be able to reproduce those back in a development environment. Yes, question?
So your definition of determinism was kind of end-to-end. An input, you got an output, some end state, and those are in one-to-one relationship.
Correct.
You're talking about debugging, it seems like you might be concerned about intermediate states where your definition allowed there to be multiple different intermediate states leading to the same final state.
Correct.
You going to talk about that?
Yeah, so let me just repeat it for the recording. So the question is there is a notion of sort of just input-output determinism that I've described, that maybe during production all we care about is we provide the inputs, we get the same output. But during debugging, we would also care about maybe the intermediate states in the computation that were used to derive that final output. Yes, that's a great point. So I will touch upon that a little bit later, as you'll see as I describe the systems and how they actually work, that we do provide that series of deterministic intermediate states as well, which I do think is crucial for debugging. Great. So many others have identified these as useful properties for systems research. So there's been a lot of related work that provides these same benefits, but in a more limited fashion. So for example, there's been a large amount of work on record and replay systems, both in hardware and also in software, and also hybrid hardware-software systems. Some of this technology is actually transferred over to the commercial realm. So these days, it's not uncommon for hypervisors and also debuggers to allow you to execute programs in reverse or allow you to replay an execution. Currently, the commercial products only allow record and replay for single-threaded programs. So multi-threaded record and replay is still considered an open research problem. On the testing side of things, no doubt many of you will be familiar with the work that comes up with smarter testing strategies, so ways to examine all of the schedules that are possible for a given input, and ways to intelligently explore that space. There's also been work on what's called constrained execution. So the idea here is that we test our program, right, and we explore through testing a certain part of the space of possible schedules. And then when we go and deploy our program, we might like to sort of limit its execution to that part of the space that we've tested before. So constrained execution is a mechanism for, in a best effort way, kind of trying to limit the code to doing what we've tested it doing. So in contrast to these point solutions, determinism provides a unified mechanism, right? It's a single mechanism that provides all of these benefits. There have been other approaches to determinism as well, however. So one of the most popular has been this idea of language-level determinism. So the basic idea here, this is a new programming language, something like deterministic parallel Java or Nestle, if you're familiar with those. And the basic idea is let's have a new programming language which is constrained in the kind of parallelism that it can express. Often there's a heavy emphasis on static checking as well. And what we will do is that we'll design the language such that all programs that are expressed in such a language are deterministic by construction. So that's the trade-off that you make. You have to rewrite your program in this new language. It only supports restricted forms of parallelism, but it gives you determinism by construction. Another interesting, somewhat bizarre use case of determinism came up with, of all places, the Halo game engine. So Halo is as you at Microsoft well know, a very popular first-person shooter for the Xbox. And it turns out that in speaking with the Halo developers, the Halo engine has been explicitly architected to run in a deterministic way since back in 2001. And so Halo is multi-threaded, running on the Xbox as well as the GPU. And the reason that the Halo developers did this was for all of the good software engineering reasons that I described previously. But also, determinism enables some new use cases in the context of their game engine. So for example, when you are recording a game session in Halo, you can efficiently do that recording by just logging the explicit network and controller inputs, right? You don't have to record anything else about the execution. And then later on, when you watch that game session again, you aren't just seeing a movie. You're actually experiencing a deterministic re-execution of that previous session. And so this allows you, as a user, to interact with the game world in certain non-intrusive ways. So for example, you can move the camera around. And you can also re-render that session at higher resolution if you want. And because the underlying platform is deterministic, you have a guarantee that when you re-execute it, even with this non-intrusive instrumentation, no divergence will occur, right? And if Halo was a non-deterministic execution platform, obviously all sorts of things could go wrong during the replay process. So in contrast to these two approaches that we've seen, so the Halo developers were just using manual best effort approaches. They stuck to deterministic parallelism patterns, they tried to avoid data races in their C++ code, and they hoped for the best. So that's the sort of manual approach. We could also write all of our code in these deterministic languages, but they have various restrictions as well. So in contrast to these two previous approaches, what I'll show you today is this idea of execution level determinism. And so execution level determinism is a completely automated approach. There's no need for a programmer to do anything to their code for it to run on this platform in a deterministic way. All right, so that's the first bit. So now let's move on. How do we actually provide determinism? Well, let's go back to this idea of our multi-threaded voting machine, right? So we had these different interleavings of instructions here, and we saw some examples of how they could arise. But in order to control the program's output, we need to control this interleaving in some way. And so the basic idea is we're going to isolate the instructions from each thread from all of the other threads. So we're going to isolate them in terms of the memory that they read and write. So it's a shared memory program, but we isolate each thread from all the other threads. Basically, what this is doing is it's taking a multi-threaded program and converting it into a collection of single-threaded programs, right? And so each of these single-threaded programs is going to naturally execute in a deterministic way. And so that's how we can get determinism from a multi-threaded code. Now, obviously, threads want to communicate with each other, right? That was the whole point of writing a multi-threaded program in the first place. So we need to handle these updates. What we need to do is we need to merge updates in a deterministic way and at deterministic times or points in the execution. And then to execute an arbitrary parallel program, we can just lather, rinse, repeat this process until termination. So this is the determinism recipe that we're going to follow today. We need to isolate threads updates from each other. We need to merge updates in a deterministic way and at deterministic times. And as you'll see, we have a series of optimizations, but we can come back to this recipe each time and see how it provides determinism and how we can change the mechanisms to provide different performance.
But if there's a conflict between the two, you might have to, well, if you are interested in providing sequential consistency.
That's right.
Just merging updates in a deterministic way is not enough.
Right. So we'll see the first scheme I'll talk about uses transactional memory. It does provide sequential consistency. We'll show how to handle those conflicts. And then later on, I will argue that we maybe should give up on sequential consistency, move to more relaxed consistency, but we don't have to give up on determinism in that context. All right, so let's start with the simplest possible thing, right? Serializing the program. So this is an execution timeline diagram. I'm going to show you a bunch of these throughout the talk today. We've got time on the x-axis, and then threads are on the y-axis. And what we're going to do is we just execute one thread at a time, switching between them in a round-robin order. Now, the things we have to enforce in order to ensure determinism, so we have these, each thread executes a set of instructions. We call that a quantum. And then the amount of time that it takes for each thread to execute a quantum, we call a quantum round. And to enforce determinism here, we need to ensure that quanta are of a deterministic size. So they're typically on the order of 10,000 instructions. And then we have to have a deterministic scheduling policy for switching from one thread to the other. So round robin is a very simple but perfectly fine example. And if we have these two properties, then we can enforce deterministic execution. To put this in terms of the recipe that I showed you previously, right, we need to isolate threads from each other. We do that by running one thread at a time. Very trivial form of isolation. We don't actually need to merge updates because, well, it's only one thread running. And then in order to switch between threads at deterministic times, we're going to count out a fixed number of instructions. All right, so this is great. This allows us to enforce deterministic execution for an arbitrary parallel program. This could be the end of my talk, right? Yes, question.
Presumably that's count fixed number of instructions, or unless the thread explicitly does a blocking call of some sort.
Yes, so there are some things you have to do if you want to handle, like if it blocks into the operating system, say, where threads are created, threads exit. Yes, but in the common case where threads are just running, this is fine. Great. I should also point out it's straightforward to handle those other cases deterministically as well because they arrive at deterministic points in each thread's execution. Great. So what's wrong here, right? There's only one simple thing that we left out, And that is, of course, all of the parallelism in the original program, right? We wrote a parallel program in the first place. That was something, obviously, that was important to us. So what we're doing is, or what we would like to do is, we'd like to be able to somehow, magically overlap the execution of these quanta, right? Because we started with a parallel program. Parallelizing parallel code should be relatively straightforward, right? Much easier than parallelizing sequential code. So as an architect, whenever I hear that we need some kind of magic mechanism to overlap these quanta, I think, OK, that's pretty straightforward. We'll just go ahead and speculate. And the particular speculation mechanism that we're going to use is called hardware transactional memory. So many of you are no doubt familiar with transactional memory. And it's a very sophisticated and active research area. And I don't have time to go into all the details today, but I will tell you the 3 things you need to know about transactions to follow the rest of this talk. So the first thing is that programmers place code inside transactions. The second thing is that the semantics of these transactions are such that the code running inside a transaction is under the illusion that it's executing completely serially. It's like it's the only code running in the entire system. Now, in reality, there may be other transactions running concurrently, but this is the illusion that you as a programmer can rely upon. The second thing we need to know about transactions is that they're implemented using speculation, particularly in the context of hardware. And so what this means is that what the runtime system will do is it will potentially launch a bunch of transactions all running concurrently. It will check for interference between these transactions as they run. If there's no interference by the end of a transaction, then that transaction can go ahead and commit. However, if there is some interference that's detected, then that transaction will roll back. It'll be as if it never executed in the first place. All right, so in terms of our recipe, how does this all fit together? Well, we're going to isolate threads from each other by taking these quanta and putting them inside transactions. In order to merge updates in a deterministic way, we're going to enforce that these quanta commit in a deterministic order. And then in order to switch between threads at deterministic times, we'll just count instructions like before. OK, so let's see. Yes. So I should also point out that there are actually 3 criteria that determine when a thread's quantum ends. One is hitting a fixed instruction count. The others deal with synchronization and also with exhausting finite hardware resources. And I'll get to those later in the talk. All right, so let's see an example of how this all fits together. So we're going to execute quanta in parallel, right, because they're implicitly running inside these transactions. After the quanta are done executing, we go ahead and commit them in some sort of fixed deterministic order. So that's what commit mode does. So there's 2 things that are important about commit mode. One is that it's enforcing the illusion of serial execution, right? So this is exactly equivalent to the straightforward serialization that we saw previously. And that's because we're forcing a commit in a particular order. The second thing that's important about commit mode I'll actually get to in just a second, but that fixed order can actually help us optimize a bunch of the conflict detection mechanism as well. OK, so what happens if we have one of these conflicts? Well, let's say we have a conflict between thread 1 and thread 2. What we're going to do is we will detect that conflict. We will roll back, in this case, the transaction running on thread 2, re-execute it during commit mode, and then continue executing from there. So again, this maintains that illusion of serial order that we started with. So let's dig into conflict detection a little bit here, right? So as you're probably familiar with, conflicts are defined as 2 operations from, say, 2 different threads or 2 different cores accessing the same memory location, and at least one of those operations is a write. So that's the standard definition of a conflict from the transactional memory literature, and that's reified in this table here. Now, when we get to our deterministic transactional memory system, it turns out that we can be much more relaxed in detecting conflicts. So how does this work? Well, the basic idea is that for these 2 rows that I've highlighted here, we have a write operation as the second operation. So this write operation is always going to produce the same value for a location because we're executing deterministically. The write operation will always be ordered as the second thing, again, because of our deterministic commit order. So we could roll back and re-execute in these cases, but we would always end up with the same value same final value anyway. So there's no point in doing that. So let's just not detect a conflict there. Of course, there's still this other case where we have actual data flow between operations, and that does require a conflict. And let me just dig into that a little bit. So let's say thread 2 is writing location x, thread 3 is reading location x. Right? Thread 2's value is locked up inside its transaction. So thread 3 is going to see some previous value for x from somewhere else in the system. Then if we detect a conflict, roll back, and then re-execute the transaction on thread 3, we can see that the commit here from thread 2 has made that new value of x visible. So this re-executed version here is what conforms to that illusion of serial execution that we wanted. Right? We want the illusion that thread 3 executed after thread 2. And so because re-execution generates a different result, we have to detect a conflict and roll back. OK, well, we don't actually have to do that all of the time. So let's just take a step back and see how we could optimize this a little bit more. So thread 2 is producing this new value for x, right? And it's trapped inside the transaction. But in some sense, we don't want it to be trapped inside anymore, because that's precisely the value that thread 3 needs to see. So if there was a way that we could sort of poke a hole in that isolation, let the value leak out, then we could potentially optimize away a rollback in this case. So the general idea is that let's break isolation. This will help us avoid rollbacks. This doesn't work in all cases. It could be the case, for example, that thread 2 later writes another value to x. Yeah, and so we would have to detect that we had forwarded the wrong value and still roll back and re-execute in that case. But ultimately, this means that many of the situations in which we would normally have to detect a conflict, we no longer have to detect a conflict. Yes?
In that case, you would also have to, you may have introduced seg faults and stuff in thread 3, even if they didn't exist in the correct program.
Yes, that's correct. That execution, or the control flow could diverge arbitrarily due to reading the wrong value. Yes?
So I guess I'm not sure I understand. So how do you know, in terms of when you break this isolation, where the visibility of the write is in the third transaction? And doesn't it matter where it shows up in terms of the ordering of the instructions within the transaction?
Which gets you back to what do you think about all the interleavings?
Correct. So,
Yeah.
So maybe if I understand your question correctly, you're asking about when exactly do we do the forwarding, and can't that affect the, I guess so if we had multiple reads going on in thread 3, which of them will see the value? That's correct. So what we're doing here is we're still enforcing the illusion of serial execution of these quanta. So the way that, I didn't go into the details, but the way that we would detect conflicts and the need to roll back, even in this more advanced speculative forwarding scheme, would be to ensure that we always had the illusion that it was thread 1's quantum, then thread 2's, then thread 3.
No reads to x occurred before the value that was written is forwarded. Is that
Exactly.
So in terms of, if you recorded the happens before graph, you would say that there was a dependence from T2 to T3, but that was okay because of the order, because it was consistent with the order I would have imposed for determinism. But
Correct.
if you saw T2 ordered before T3 and T3 before T2,
Then you have a cycle.
then you'd have a cycle.
It's not.
So are you like
serializable.
piggybacking? So do you like piggyback a little bit on the conflict detection to do that? How does that work? Do you need to extend the HTM to sort of do this?
Right.
linkage?
Okay. So the question is, how does this more sophisticated conflict detection work? So yes, you can extend hardware transactional memory's conflict detection to detect these kinds of errors, or not these errors, but these kinds of essentially serializability violations as well.
But do you have to know in advance sort of the set of threads in the order you want to resolve conflicts in order to do this?
Yes,
You do.
knowing the order in advance is crucial, because then we know,
Right.
that lets us know that, okay, forwarding from this thread to this thread is okay, or that it should have been the other way and we need to
I see, cool.
roll back. Great. So just to summarize how this transactional memory scheme works, I've shown you how we can recover parallelism from a parallel program using hardware transactional memory. I've shown how we can avoid rollbacks in many cases by optimizing the conflict detection process. And then the final thing is really something that would be nice to have but that we don't have, which is that it would be really nice if we could avoid this need for constant speculation. Right? We're putting every instruction in the program inside a transaction, constantly speculating. And as you're well aware, speculation has many costs. Right? There's the time and the energy that you lose whenever you misspeculate. But then, in some sense, something even worse is just the complexity of implementing the speculative machinery in the first place. Right? What do we do about irrevocable actions? Because everything is running inside a transaction, we need some other out-of-band mechanism to handle things like I/O. So if we go back to this recipe for determinism using transactions, we can see that it gave us everything that we needed in order to provide determinism. But it also gave us something that we didn't need. Right? It gave us this serial execution, which was enforced through speculation. And we really don't need this illusion of serial execution. In some sense, transactions are really overkill. So they give us this nice serial order, but if all we care about is determinism, it would be totally OK to have a more sophisticated interleaving of instructions, as long as we maintain determinism. So the hope here is that we can come up with a scheme that provides the performance of transactions in terms of still expressing or harnessing the underlying parallelism of the application, but that it avoids the downsides of speculation. Now, of course, it's important to maintain two properties. One is we still have to be deterministic. That's the whole point here, of course. And the second thing is that we have to maintain program semantics. Right? So reordering instructions in very sophisticated ways may break existing code. And so we want to make sure that we still support existing parallel programs. So I'll talk about these 2 points in turn. So the first thing I'd like to explain, though, is this notion of a store buffer. So this is a bit of a detour into how processors are implemented. And we'll see that this is important for understanding how we can enforce determinism in a non-speculative way. All right, so store buffers arise because we have the situation, say, where a processor is doing a store, and that store misses in the memory hierarchy. So there's kind of two options we have here. The very simple thing to do would be to say, all right, we'll just sit around and wait. And as soon as the cache line that we need percolates into the L1, then we will allow that store to complete, and then keep on executing. But if you think about what a store is doing, right, it's just producing a value, sending it to the memory system. There's nothing that we need from the memory system in order to continue executing. So why not have a little hardware structure that sits here, buffers the operation coming out of the processor, and then lets us keep going. Right? We have to remember that value so that way subsequent loads can still see it. But really, there's no need to stop and block the entire core just because we missed on a store. So for our purposes, store buffers are really nice because they provide isolation without any kind of speculation. So there's nothing speculative about using a store buffer. If you have a store, you just put it into the store buffer. Subsequent loads check that store buffer, but you never detect conflicts. You never roll back. I should also point out the store buffers are private to each processor. Right, so P2 can see its own stores, but P1 has its own separate store buffer. It doesn't see what P2 has done. Great, so in terms of our determinism recipe, now if we want to eliminate speculation, we're going to use store buffers to isolate threads updates from each other. In order to merge updates in a deterministic way, we came up with a parallel merge algorithm, which it turns out is exactly the same as the Z-buffer algorithm that's very common in graphics hardware. And then, of course, we'll count instructions like before. Now, I don't have time to go into this parallel merge algorithm. I'd be happy to talk more with you about that offline. But I will go into store buffers and how we use those to buffer updates. OK, so we're executing in parallel again. We're using store buffers to isolate threads from each other. I should also point out that we have a way of performing synchronization in parallel mode as well. This is due to a nice algorithm from some folks at MIT called Kendo. And I won't have time to explain that today, but I can share the details offline. OK, so how does the store buffer mechanism work? Well, let's say thread 1 is writing to location A. Thread 2 is reading from it. Thread 2 is going to get some previous value of A. Right? It's not going to see thread 1's update. Thread 1 will see its own updates, of course. Otherwise, things would get pretty crazy. And if thread 2 also wants to update location A, that's fine. It gets its own private copy, can do whatever it wants with that. After we're done executing in parallel, we have commit mode, which deterministically publishes the contents of each thread's store buffer, making it visible to the rest of the system. That uses that Z-buffer algorithm that I mentioned previously. And yes, and then we just continue executing. So one thing maybe some of you are curious about at this point. Is there a question? Or? All right. Yes?
Yeah, so you still have this quanta of 10,000 instructions.
Yes, that's right.
And so what are you assuming about the size of the store buffers?
So it depends on whether you're implementing them in hardware and software. But in terms of hardware, we use the private levels of the cache hierarchy. And so private L1, private L2s if available. And so that gives us on the order of 100, 200K.
Okay, so you basically
space.
extend the notion of the store buffer
Yes.
in your algorithms into the cache.
Right. Yes. It's yeah. We couldn't.
Right. The store buffer is just a little cache, and you make it big, but you extend the notion of the local.
Right. So the term store buffer, as applied to current processor design, is generally a very small,
Right.
maybe 8-entry structure. Right. And we need something that's much larger than that. But it's the same idea. Okay. Great. So one thing maybe that you're wondering about is that what we've done to this program is we've taken all of its updates, right, and we've hidden them inside the store buffer so no one else can see them. And is this okay, right? Obviously, we need to make sure that these updates are visible at some point, right? And so really what we're talking about now is the memory consistency model of the programming language the program was written in, and also the architecture for implementing this in hardware. So for our purposes, the memory consistency model says when these store buffers have to be made visible, when their contents need to be published. Just a bit of terminology. Publishing less often means that we have a more relaxed consistency model. Publishing more frequently means that we have a stricter consistency model. So in terms of the consistency ramifications of the scheme I just described to you, it really comes down to commit mode, right? So commit mode is what publishes the contents of the store buffer. It's kind of like a fence in, say, a current non-deterministic system. Unfortunately, commit mode is somewhat expensive because we have this global barrier, right? We have to wait until everyone has finished their quantum until we can go ahead and commit. So because commit mode is so expensive, what we ultimately want is we want a really relaxed consistency model. Because the more relaxed a consistency model is, the fewer restrictions it places on the program in terms of when updates need to be visible. Right? We want as much flexibility there as possible. So we want the most relaxed consistency model that we could possibly get away with, because we want to publish as rarely as possible. Just an interesting side note, you'd think that as an academic, I might be interested in publishing as frequently as possible. But it turns out in this particular context, publishing rarely is exactly the right idea. On a more serious note, deterministic synchronization, because it has this global visibility aspect to it, is more expensive than non-deterministic synchronization. And so, as hopefully you'll take away from this later, relaxing the memory consistency model is something that definitely makes sense in the non-deterministic context, but it makes even more sense in the context of determinism because synchronization is more expensive. All right, so which consistency model are we going to choose? Well, there's a bunch of them out there. I've just listed a handful on this slide. As I said, we want the most relaxed consistency model as opposed to the most uptight possible. So we're going to choose what's called data race-free 0. It's essentially the same consistency model in the C++ memory model or Java. So let me just give you a quick gloss on how the DRF0 model works. Right, so say we've got these two threads. They're executing these instructions. DRF0 says that visibility has to be propagated along these happens before edges. So happens before edge is something that maps up that matches a release operation of a lock to the subsequent acquire. And so DRF0 says that updates have to be visible along these edges, and any other time you are free to keep those updates buffered. So now let's put this all together in terms of an example. So we're executing in parallel, right? We can do synchronization operations in parallel as well, thanks to the Kendo algorithm. Then we have a commit mode. We continue executing. Let's say that thread 2 unlocked this lock, and then thread 3 subsequently locked it, right? So we've got a happens before edge here from thread 2 to thread 3. Our consistency model says that we have to ensure that updates are visible along one of these happens before edges fortunately, for my example, we have a commit mode that exactly intervenes, right? And so this commit mode satisfies the constraints of the consistency model. So it turns out that this is a relatively common pattern in the benchmarks that we looked at. And ultimately, it means that we are rarely forcing a commit mode, which is expensive, due to synchronization constraints. Our consistency model is relaxed enough that that rarely comes up. And so what this allows us to do is it allows us to execute larger and larger quanta without having one of these commit modes intervene. And so because we can execute larger quanta, we can better amortize the cost of these barriers at the end of each quantum round. And this ultimately gives us higher performance. So just to summarize this relaxed consistency approach to determinism, I've shown you how we can still execute programs in parallel in a deterministic way without relying on speculation. The key to that was adopting a relaxed memory consistency model. And I hope I've also convinced you that relaxed consistency is a very natural optimization for determinism because deterministic synchronization is so much more expensive than its non-deterministic variant. All right, so that does it for the algorithm section. Now let's talk about how do you actually build this stuff, right? And then I'll show you some graphs at the end of this from some of the systems that I've built. So if we go back to the transactional memory implementation, what we started with was a conventional multicore processor. And the first thing we needed was a best effort hardware transactional memory system, very similar to what Intel has said is coming out in their Haswell processors next year. And then in addition to this best effort HTM machinery, we also need a little bit of extra stuff. We need quantum building inside the processor core. We need to count instructions. We need to enforce a deterministic commit order of transactions. And then finally, we also need to ensure that if we overflow the resources of the deterministic transactional memory hardware, which is typically implemented in the private cache, we need to ensure that that's a deterministic event, so that way we can use that as a signal for when a thread should stop its quantum. And so ultimately, this boils down to modifying the cache eviction policy a little bit. So when we moved from the transactional memory implementation to the relaxed consistency implementation, we realized that, well, first of all, we don't need hardware transactional memory anymore, right? And because that was the majority of our hardware support, we realized we had an opportunity to kind of strip down the other mechanisms that we needed in hardware as well. So at the end of the day, we got it down to just these three mechanisms. So the first is instruction counting. I think instruction counting makes a lot of sense in hardware. It's really cheap, and it has a non-negligible cost in hardware. In software, right? And so the second mechanism we use is we require a store buffer mechanism, trying to leverage the private caches on the system, right? We want to keep threads isolated from each other. Private caches are isolated at the hardware level, so it makes a lot of sense to reuse that physical isolation at a higher level of the stack. Question?
Maybe this is totally off the subject, but there's speculation going on inside the hardware itself, right?
That's correct.
And
Sure.
depending on the state of the cache and things like that, the same instruction sequence may or may not take more cycles, I guess. But at the level of the individual instructions, you're saying it's completely deterministic. Is that right?
Right. So as you point out, there's a lot of speculation going on under the covers, and the decisions used to inform that speculation are not necessarily deterministic. Right. So ultimately, we have a deterministic outcome for a program, but we don't necessarily have deterministic timing for that program. Yes, and so I will gesture towards some ideas in the future work section about how we might go about building a processor that has deterministic timing, and from that you would also get a deterministic outcome as well. Great, so the third mechanism that we need is this, so the parallel merge algorithm that I didn't describe has a lot of fine-grained parallelism. It's implemented in hardware and GPUs, and it makes a lot of sense to bake that into hardware for our purposes as well. On the software side of things, we try to leave as many policy decisions as possible up to software, right? So issues about how big quanta should be, maybe whether they should adaptively grow and shrink over the course of an execution, that's all up to software. Issues about when to place a particular store value into the store buffer or not, because you can leverage static analysis to prove for certain locations you don't need to do that. And then finally, issues about when the contents of the store buffer should exactly be made visible. So basically, the question of enforcing the consistency model, because it's a relatively rare occurrence, we also leave that up to software. So now I'll show you some results, first from a hardware simulator that we built to simulate this processor design. There's a lot of details here. Source code is available on our group website. But ultimately, you care about the results, right? So we've got benchmarks on the x-axis, and the y-axis is performance overhead that's normalized to non-deterministic execution. So the baseline is, let's take a non-deterministic program, so just basic pthreads plus locks, run it on our simulator with, say, 4 threads. That's the baseline. How much does determinism cost you on top of that? And so here are the results from our hardware simulator. As you can see, overhead varies substantially by benchmark. But even when we're looking at a 16-processor system, the worst case overhead is in the 50 to 60% range, which we think is relatively tolerable. These same ideas also lend themselves to a compiler implementation. So we have a C++ compiler built around LLVM. In order to isolate threads from each other, we use hash tables attached to each thread. So on a store, a thread will put a new entry in the hash table, and then on a load, it checks the hash table to see if there's some value. If there's nothing in the hash table, then it goes out to the read-only version of main memory. And then we've implemented the commit mode algorithm as well in software. So it's the same setup as before. Performance is normalized to non-deterministic execution. Because this is all pure software, these are experiments running on a real machine in our lab. As you can see by the scale of the y-axis, the performance overheads are not quite as rosy. And indeed, there are some benchmarks that show roughly an order of magnitude slowdown for enforcing deterministic execution. Yes?
So you haven't really said anything about how scalability is affected. It looks like in some cases you get, like StreamCL, you actually get higher overheads with more processors. Is that generally? I'm curious.
Yeah, I think scalability is an interesting point. So there's sort of 2 answers there. One is that the store buffer instrumentation that we add to the program is relatively scalable, because that's something that each thread does in isolation. And so one thing you notice on the hardware results is that for some benchmarks, the overhead reduces as we increase the number of threads. And that's because we're normalizing to a non-deterministic baseline. And the non-deterministic program doesn't scale perfectly. We add a bunch of overhead to the program, some of which does scale quite well.
Okay, but that's kind of hiding the fact that there's an underlying non-scalable aspect of the program, right? So in some sense,
Correct.
the fact that, like in VIPs, the fact that it went down is really just it's more to the fact that this program won't scale on 60 processors no matter what you do in some sense, right?
Right.
Yeah.
And so, yes, and so ultimately you would want to re-architect the fundamental program to scale better.
Scale up to 16, you'd have an even higher overhead in VIPs with this approach.
Correct. So the thing where scalability really starts to affect us is in terms of these global barriers at the end of each quantum round. Obviously, stopping all threads, forcing them to synchronize is not the way to scalability. So I do have some ideas about a more scalable deterministic algorithm, which I haven't gotten around to implementing yet, but that eliminates this need for global barriers. All right, so I've shown you that hardware determinism can be quite fast, right? But obviously it doesn't exist unless you have $1 billion or so lying around. You just want to give to me. I'd be happy to go off and fab this for you. Software determinism does exist, but as we can see, it's quite slow. And so ultimately, we would want some way of improving the software performance, right? And so that's what I'm going to talk about next. And I'll make this relatively quick, because I know I'm running a little bit tight on time here. So the current thing I'm working on is this project called MELD. So MELD stands for Merging Execution and Language Level Determinism. So as I gestured to at the beginning of the talk, there are these sort of 2 camps to providing deterministic execution. There's the language level approaches, which have existed for many years, and then there's the execution level approach, which I described to you earlier today. So these 2 approaches have, in many ways, a classic static versus dynamic analysis kind of trade-off. right? So if we do things statically, there's no runtime overhead, but things are going to be more restricted, right? And so a dynamic approach can handle the general case, but we have to do everything at runtime, so it's more expensive. Another interesting point of distinction between these two approaches is that the restrictions that deterministic languages enforce allow them to have this property known as sequential semantics. So sequential semantics is this really nice property where your program is going to have the same exact behavior if you run it with 1 thread or 10 threads or 1,000 threads. And that really comes about because of the restrictions in the language. If we think about a dynamic approach where we are supporting arbitrary multi-threaded programs, right, there's no way to get that same kind of agnosticism to the number of threads the program is using. Because fundamentally, you could have a program that does something completely different with 8 threads versus 7 threads, right? So there's no way to really abstract away the number of threads you're using. So MELD is a hybrid approach, which tries to combine the best of both worlds in terms of the static and dynamic techniques. So we end up with low runtime overhead, as I'll show you, general support for arbitrary parallel programs, but because of that generality, we are not going to be able to provide sequential semantics. All right, so the motivation behind MELD is this so-called 90-10 rule, right? 90% of the time spent in 10% of the code. For a lot of parallel programs we looked at, it turns out that this 10% of the code is often data parallel in a nicely structured way. So here's a little cartoon of a parallel program. So there's lots of complicated stuff going on, maybe locks, flag-based synchronization. But there's this little kernel of regular data parallel computation buried underneath all of this complexity. And fortunately, for our purposes, this regular data parallel kernel is often where a lot of the time is spent, perhaps because this is a fundamentally more, or typically a more scalable kind of parallelism than something a little bit less structured. So the basic idea behind MELD is let's use execution level determinism to handle all this complicated stuff, right? And then let's use a deterministic language for encoding this very regular computation, which seems pretty straightforward. Of course, the tricky part is what's the interface between these two approaches? Because there's many things that could go wrong if we don't think about this carefully. So let's say we have some kind of parallel merge sort algorithm, right? Standard divide and conquer parallelism. We could write this in a deterministic language, like deterministic parallel Java. It'd be very straightforward. And we could verify it in isolation. But as soon as we take that isolated function and then plug it into a larger program, all sorts of interesting issues come up, right? Are there concurrent calls to merge sort? What aliases are input here? Can other threads, modify array while we are modifying it? The whole point was to, statically verify this as deterministic, remove all instrumentation, and in order to answer these questions, we would naively add back a lot of instrumentation. So what do we do with MELD? Well, we propose a lightweight type qualifier system, which essentially segregates the data in the program into the part that's operated on by the deterministic language and the rest of it. And then we have a simple set of typing rules which enforce certain aliasing properties so that you can't just take a pointer from one side of the world and then publish it onto the other side. So here's a quick diagram of how the MELD compiler works. So we've got our program. It's got its little data parallel kernel. And we've got the type qualifier system to keep them ring-fenced. So we take the complicated parts of the code, run that through our standard deterministic compiler, so that adds the store buffer instrumentation to all of the memory accesses. And then for the data parallel kernel, we do two things. First, it's written in a deterministic language. And so what we do is we take that code along with what we call an abstraction. Currently, this is done manually by yours truly, but we are looking into automating this going forward. The abstraction is basically just a conservative summary of what else is going on in parallel with this data parallel computation. So it may be the case that there's nothing else going on. It may be the case that there's an I/O thread running in the background, something like that. And basically what we do is we take this abstraction and the kernel, we express them both in a deterministic language. And then if we can get that code to compile, then we have a proof that it's safe for those two components to run in parallel without instrumentation.
Isn't it going to be the case that usually the thing that is running in parallel with this kernel thing is completely isolated from it? They're operating on different pieces of memory and whatnot. Is that not true? Mostly? Yes,
and which is fortunate because we need to be able to express that isolation in a static way. So that limits the amount of reasoning we can do. But yes, that is true. And then for performance reasons, we found that it's good to count instructions everywhere. We're still building quanta because we're doing the standard execution level determinism approach. And because we don't, for load balance purposes, it's hard to know a priori whether we'll have all of the threads running something that is in a deterministic language or not. So we just count instructions everywhere. And that turns out to be the best approach for performance. All right, so now I'll show you some results. Again, benchmarks on the x-axis here. We're also normalizing overhead to nondeterminism like before. And these are experiments run on a real machine. All right, so these are the blue bars I showed you previously for our deterministic compiler. And as you can see in the green here, that if we are able to leverage these well-structured kernels of data parallel computation, we can remove a dramatic amount of the runtime instrumentation that we're doing. So I think this is a really promising approach moving forward.
But do these programs, do they even have any of the other kind of stuff? The crazy stuff?
Yes, they do. So we have a workshop paper about this if you're interested in more details. I can also talk with you more offline. But yes, so we have a table there showing that these programs do acquire locks, use condition variables, and so forth. And so obviously, parts of the program can be expressed very cleanly in a deterministic language, but it would be non-trivial to take the entire code and port it over. All right, so just to summarize the contributions I've talked about today. First of all, at UW, we pioneered a set of techniques that provide determinism for arbitrary parallel programs, so even programs that have data races in them. I've also shown you that relaxed memory consistency is a very natural optimization for determinism because of the cost of deterministic synchronization. I showed you how to implement determinism across the stack, right? Which parts are really amenable to hardware support, which should live in the compiler, and which maybe even have a good case for modifying the language. So now I'd like to talk about future work. Since I work in the area of determinism, you might suspect that all of my future work is strictly defined in terms of things that I've already done. And you would be somewhat correct. So I am very interested in using determinism to improve program safety and performance. But looking more broadly, I'm also really excited about this notion, what I'm calling safe memory. And so this is an idea to battle some of the upcoming programmability challenges I see coming with emerging processor architectures. So let's start with determinism. So one of the things I'm excited about is new use cases for determinism. So one of the things that's nice about determinism is it lets you run multiple copies of a multi-threaded program, and so essentially doing replication. And you can keep those replicas in sync very easily just by broadcasting the inputs, right? Because you know that the replicas won't diverge on their own accord because of determinism. So I think this is going to be useful in many ways. One particular way is that if we are trying to analyze some multi-threaded execution, right? Let's say we want to detect races, we want to track information flow, we want to turn on expensive contracts, checking, something like that. Typically, what we'd have to do is just layer all of those analyses onto a single execution, right? That's the only way that we could get a sound union of all those guarantees, right? But now that we can replicate a program efficiently using determinism, right, we can turn on one analysis in each replica, right? So we only pay the overhead of say, the slowest analysis. It's possible to go even further, that we could take a particular analysis, right, and essentially stripe it across multiple replicas. And if we're smart about how we do the sampling within each replica, we could construct a scheme where we ended up with the same full coverage guarantees, but we don't pay for the execution overhead in any particular replica. I also think it's useful to think about re-leveraging the isolation that we are using to enforce determinism in other parts of the programming stack. So definitely inside the runtime system, one can imagine using this isolation to maybe allied synchronization, enable new compiler optimizations. It's possible that this could even be useful at a programming model level, so possibly part of the programming language as well. On the other end of the stack, getting back to Ben's question earlier, all of the systems I've talked to you about today provide deterministic output, but they don't provide deterministic timing. And so that would be an interesting avenue for future research, right? There's many, particularly in the real-time systems community, people who care a lot about deterministic performance. And I think that there's a large overlap in the mechanisms that can be used to provide deterministic timing. And they could also, with slight modification, be sort of, turned down a little bit to allow just a deterministic outcome if you wanted to provide both sets of guarantees. Another thing that I think is interesting is that in terms of information flow security, there's also another point of connection, that the non-determinism that people are concerned about eliminating in information flow security, right, so you want to stop timing channels in that case, is very similar to the kinds of non-determinism that the systems I've described today are eliminating. So in some sense, you could think of the execution level determinism stuff I've described to you as providing a very low level of information flow security, right? It's preventing certain flows of information because we fix the flow of data within the program. And so that could eliminate certain channels. And then information flow security, eliminating timing channels, eliminating propagation from, trusted to untrusted data is a generalization of that idea. All right, so on to safe memory. So we're all familiar with Moore's law, right? Exponentially more transistors over time. Historically, this has led to increased single-thread performance, right? We got faster processors. More recently, this has shifted into providing more cores on a particular chip. And in the future, we're going to see multiple accelerators, special purpose accelerators, living on the same chip along with multiple cores. And fundamentally, these phase shifts have been driven by the power demands of processors, right? So because we couldn't scale frequency anymore, we shifted from a single core to multiple cores. And increasingly, we're seeing that because even though we get exponentially more transistors, the power used by each transistor is relatively constant, even though they're getting smaller. This means that if we kept all the transistors on all of the time, we would have exponentially increasing power per chip, which is obviously not particularly sustainable. And so that's leading a trend towards specialization. So we've got special purpose accelerators that we use some of the time. Most of the time that they're off, they are off. And so this allows the entire chip to stay within its power budget. So what do these accelerators look like? Well, there's going to be multi-cores, obviously. I don't think those are going away. GPUs are now integrated on chip. And we could also, in the future, who knows what those crazy architects will come up with, right? Crypto, reconfigurable, there's many possibilities. Unfortunately, for a variety of reasons, I think that these accelerators are going to be more or less black boxes. I think there's an intellectual property argument here. But also, because these accelerators are designed for low power operation, it doesn't really make sense to add a lot of extra stuff so that you can see what's going on inside these accelerators. Right? So these are black boxes of functionality. And because there's no visibility here, I think there's going to be a great programming challenge that is similar to the multi-core programming challenge that we faced, but in some sense much worse, because we can't instrument the code that's running on these accelerators. Yes?
Can you contrast this kind of thing with the system on a chip? How is a system on a chip not exactly the same story?
It is exactly this same story.
But you can buy phones today that have hundreds of millions of phones that don't have the programmability challenge, arguably.
Right. I think that basically, so system on chip definitely exhibits some of these trends. I think that going forward, as we have more and more transistors that we need to burn, I think that the sort of scope of each particular accelerator will become much more specialized. And so because these things will become very specialized, maybe you would use it to accelerate part of the garbage collection algorithm or part of this data structure operation. And so they'll be woven into the program in much more complicated ways than they are currently.
AMD
Yes.
has a proposal to make the GPU eventually context switchable. And it's going to read and write shared memory, so we get away from this isolated device driver model.
Correct.
What do you think about that sort of approach?
Yeah, so the question is about AMD's plans to bring GPUs on chip. So shared memory is already here with some of the Fusion coprocessors. And then, yes, certainly the OS people want to virtualize things too.
These transistors, I mean, we really want to develop these programs efficiently. I guess it goes back to an old argument with even single CPU, why should a hardware designer put budget in for debuggability and programmability? So
Right.
you're arguing that in this world it'll just performance will trump it, and we still, with these new types of chips, we don't have, you know, all the debuggability extensions and everything we see.
Right. So the question is, how much debuggability, you know, logic or budget should we add to each one of these accelerators? And I think that answer is very little, and I think historically that's been the case too. But I have a new, perhaps, idea about where we should spend some of that complexity. Right. So just to flip quickly through all the problems that you're certainly familiar with, right? So we've got data races, atomicity violations, memory safety issues, right? I think we'll have new kinds of bugs around resource brokering, right? How do you ensure that only one person is using an accelerator at a time? How do you do debugging across code that runs partially on the CPU and then steps over into one of these accelerators?
What is resource brokering?
Just ensuring that, say, if you had a reconfigurable logic, right? You want to ensure that only one person is using that at a time,
Okay.
that they don't have conflicting configurations, and so forth. Setting up, often these accelerators require a little bit of configuration before you can actually run the computation that you want, so they are configurable in a limited way. And there's certainly, I've noticed a lot in the GPU programming I've done, that there's a lot of issues that can come up with sort of speaking the right protocol to the accelerator. And I think there's a lot of opportunity for providing richer support in terms of speaking these protocols correctly. So one option we could have that we've sort of been talking about already is that we can kind of turn these black boxes into gray boxes, right? So we can peek inside a little bit, see what's going on. Maybe that'll help us figure out some of these issues. I think that a better approach, though, is to instead think in terms of the communication fabric that we use to talk to these accelerators. So for various reasons, I think this is going to be shared memory. Although I'm definitely up for a good shared memory versus message passing debate if anyone wants to join me later. Ultimately, shared memory has lots of problems, right? Hopefully I've convinced you that over the first part of this talk. And so what I think we need to do is we need to build something on top of shared memory that I'm calling safe memory that provides much more safety than shared memory does. So I think there's all kinds of specific safety properties we could build on top of shared memory as opposed to modifying each of these accelerators underneath. So we could look at ensuring that an accelerator executes code in an atomic and isolated fashion. We're definitely going to want sandboxing for security purposes. We can think about implementing watch points, which would be helpful with debugging. We can think about ways that we can use the memory interface to debug what's going on inside an accelerator, right? So we can do the debugging from the outside as opposed to from the inside. Performance isolation issues. There's lots of things that we could provide strictly in terms of this communication interface. And I think that the opportunity here is if we can do that efficiently, then we can provide these safety guarantees in a really agnostic way, right? You can take any accelerator that you want, plug it in, as long as it knows how to read and write shared memory, you're going to be fine because the communication fabric itself is providing you with certain safety and programmability guarantees. So here are just some first steps I would like to take in implementing this project. At the ISA level, obviously it's important to define what exactly the communication model is going to be, how rich is that model in terms of how accelerators communicate with each other, and then defining interesting safety properties from there. At the hardware level, we need to investigate efficient checking circuits, both in terms of the logic and then the storage that's required to enforce these safety properties. I think there's also a large opportunity to specialize the way that the network is built because these checking circuits will have very particular traffic patterns, and I think we can heavily optimize for the kind of work that they're doing. At the software level, I think that verifying the control protocols that we use to set up a computation on the accelerator and then kick it off, wait for the results, I think that there's a lot of opportunity to use maybe types or other kinds of static verification to ensure that we are speaking to these accelerators in the right way. All right, so thanks again for your attention. So to conclude, I've shown you today how we can provide determinism for arbitrary parallel programs. I've shown you how we can trade strong memory consistency for higher performance in the context of determinism. And I've also shown you how we can implement determinism across the stack, from hardware all the way up to the programming language. And then finally, I've shared some of my thoughts on this new idea for safe memory, which I think is going to be important to address the upcoming programmability challenges of emerging processor architectures. Now, I definitely didn't do all this work by myself. I'd like to thank all my collaborators that I've had over at UW and also here. And now I would be happy to take any additional questions that you have. Thanks again.
So with
Could you state your name, please?
No. Andrew Buck.
Yes.
So a few exceptions, most of the accelerators that you were pointing out, GPUs, FPGAs, any of the SoC kind of things, get a lot of performance out of managing separate memories and things that aren't in this big global memory pool of shared memory that you deal with. How do you propose addressing safe memory when a bunch of that memory is not even controlled or used in the same way as you do for a CPU?
Great. Yeah, so maybe a way of rephrasing that is how does safe memory deal with maybe caching, right? So accelerators would want to cache things for locality, for power. And yeah, I think incorporating that into the model is very important. Certainly you can get all sorts of, this is possible even with current GPUs, all sorts of weird consistency problems if you don't do the synchronization quite right. And so I think probably the most straightforward thing to do there would be to sort of hand off a chunk of data to the accelerator and then ensure that no one else tries to read or write that data until the accelerator is done with it.
Do you have any ideas about what that granularity is in terms of handoff?
I think ultimately it would need to be in terms of bytes, because I think having fine-grained protection is going to be the key to providing, to eliminating false positives, but also supporting arbitrary accelerators that maybe do something complicated to your XML string in memory, but you don't want to restrict, protect the entire page or something that string lives on.
So do you think that the notion of accelerator is going to bubble its way up into programming language abstractions?
Is the notion of an accelerator going to make it up to the PL level? Yes, I think it will. I think just as sort of an observer of the architecture community, it seems clear that a lot of the concerns which were typically kept under the covers of the ISA, concerns like energy and circuit reliability, maybe going forward even, are bubbling up. And some of them are really best handled at the programming language level. So I think something like verifying the control protocol that you use to speak to an accelerator, you could have some runtime mechanism for that, but it's something that you don't do very frequently. And when you get it wrong, it has very bizarre effects. So I think it makes a lot of sense to maybe try to reify that in the programming language and just statically check it, for example.
Any other questions? Okay.
Okay, great. Thanks again.